Math 230, Cuesta College. I'm Joe Vasta, and today we are covering section 4.4, American Standard Code for Information Interchange. So instead of saying that again and again, we will just call this ASCII, A-S-C-I-I. And sometimes people say this is ASCII code, which is redundant because it already has code within its name. Hopefully I won't say that, but it's like when people say PIN numbers and ATM machines. It's a little redundant. Okay. So a two-state device. That's what we're going to be looking at. And think of a two-state device like a light bulb or a switch. We'll say a switch that can be only on or off. Okay, so this is kind of, before we get into what ASCII is, we're going to talk about two-state device. And we have these light bulbs, and we put them on a table, and there are 8 of them. Yep. So what I'm going to do is make the realization that I can communicate information with you or to you through these light bulbs by turning some of them on and keeping some of them off. So suppose I turn this one on, so I'll go like this. So that one's on, and this light bulb's on. And what else? We have this light bulb is on, and this one right here is also on. So what I've done is I've communicated some information to you. What kind of information would that be? Well, let's go ahead and we'll write things below those light bulbs. For the light bulbs that are on, we'll just make little marks. We'll say, oh, that one's on, that one's on, that one's on, and that one's on. And for the light bulbs that are off, well, those look like 1, so the off light bulbs will have 0s. So look what I have here. I have a base 2 number, or a binary number. I'm going to convert this number to base 10. So it's easier coming back home, and this is the one where you just have to put the 1's place, the 2's place, 4's, 8, 16, 32, 64, 128. Okay, we're multiplying by 2 each time, or we're writing up the powers of 2. So to figure out what this number is, I have 0 128, so I'm not even going to write that down, and 0 64s, I have 132, so I have a 32, plus 0 16s, plus 1 8, plus 0 4s, plus 1 2, plus 1 1, so we better write that down too. And so the number looks like 43. So if I had these 8 light bulbs on a table, I could then turn them all off and then turn some other ones on and give you another number. And I can keep doing that, and maybe I assign letters to certain numbers. I could actually communicate classic novels to you. It would take a while, but I can convey a whole classic novel to you, like Romeo and Juliet or something like that, through these 8 light bulbs. And so this is the beginning of computers, because computers, they don't have a lot of light bulbs in them, but they have a lot of little switches. Okay, and the switches, you know, we have on and off. That's probably the best way of thinking of that. And so now we're going to go ahead and talk about computers. But this is the beginnings of computers, recognizing that with just 8 light bulbs, I can give you lots of information. So let's go ahead and look at our next page. Talk about computers. Now, we're not going to become like computer experts in this class, but after this lecture, you might understand your computer a little bit better than before. So computers have a lot of little switches in them, and they can be in one of 2 states. You can think of it as on or off. And each switch represents a 1 or a 0. Each switch is a bit. Okay, so we'll call the 1s and 0s bits, and bit stands for binary digit. Takes the BI there and the T from digit. So computer people sometimes do funny things like that. So let's take a look at some things that you may have heard of before. 8 bits. 8 bits equals 1 byte. So what we have right there, representing, you know, the representation with the light bulbs, that is 1 byte right there. Now, this is something we really don't need to write down, but I'm going to write it down anyway just to show you that computer people have their own sense of humor. 4 bits equals 1 nibble. Okay, so that's just what they say. Now, I'm going to show you some things that you might see on your computer or on your phone. We have 1,000 bytes equals a kilobyte, KB. 1,000 squared, that's really 1,000,000. So 1,000,000 bytes equals a megabyte. Or you could say 1,000 kilobytes equals 1 megabyte. So there's lots of ways we can do it. I'll just stick with the bytes. So if you cube it, 1,000 cube bytes, that equals a gigabyte. And then we'll go one more. 1,000 to the 4th bytes, that's a terabyte. Now, there is a bit of confusion on this. This definition here that we have of kilobyte, megabyte, gigabyte, terabyte is according to the International Systems of Units. I don't know what the abbreviation is. The International Systems of Units, and I know they have an abbreviation. So this is the technical definition of these. Now, here's the deal. You may find in some books that 1 kilobyte equals 1,024 bytes. And then 1 megabyte would equal 1,024 squared bytes. Now, why are they doing that? For historic and convenient reasons. So it's sort of a tradition with some computer science majors, and if you're studying information theory, to sometimes tweak these definitions. Now, sometimes they'll tweak the words around, but that's kind of, so I'm just saying this to you in case you hear someone say, oh, a kilobyte is 1,024 bytes. Well, they're using the traditional way that they used to. And the reason we do that is because 1024 is 2 to the 10th, and everything that way can be written in terms of powers of 2, which in terms of computer science is really nice. But if you just look up this according to the International Systems of Units, that's what those things are. And some people would argue, well, 1024 and 1000, they're almost the same. Well, you know, they're not the same, but I just thought I'd bring this up. So you can see that when you buy a computer and you're saying, well, how much memory does it have? And you're looking at, you know, gigabytes or terabytes. Really what they're doing is they're describing how many switches, how many bits. Well, really how many bytes? But we know that 8 bits is a byte. So let's continue, because what we want to do is we want to learn ASCII. Okay, so ASCII was developed in 1963. Okay, and all it was assigning symbols, letters and symbols and even numbers to certain numbers. So look at this. 65 is an A. 66 is a B. Now you might have wondered, why didn't they start at 1? They decided to start at 65. 66, 67, these go consecutive all the way. Now these are capital letters all the way to capital Z. So maybe you can pause the video and figure out what capital Z is. Okay, whether you pause the video or not, a lot of people would go, oh, well, 65 plus 26, that brings it up to 91, and they put a 91 there. But the truth is, capital Z is 90. And it's because when you add 26, you've already used 65 for A. So it's really 26 and then minus 1. And if you don't believe me, write it all out and you'll see that capital Z lands on 90. Okay. Now, we do have a little bit of a gap between the capital letters and the lowercase letters. Now, what I have over here, let me just use a darker pen here. This is just FYI. You won't be using this in your homework or on the test, but this is just for your information. The way the computer keeps 0 is by the number 48, and 1 by the number 49, and 2 by the number 50. You might pause the video and say, well, what is the number for 9? You would think 9, but no. The one for 9 is 57. The space on the computer is 32. So when you hit that space bar, it's 32. This exclamation point or mark is a 33. Question mark is 63. This at symbol is 64. So like everything you can think of has a number assigned to it. What is 91? So this is just FYI. 91 happens to be that bracket. 92 is this thing right here. 93 is the other bracket. So anything you press on the computer, I'm not going to go, 94, 95, 96 are just some other symbols. But then 97, it picks up at little a. 98, little b, or lowercase. 99, lowercase c. So pause the video and see if you can figure out what little z is. Okay, little z, if you go 97 plus 26, you end up getting like 123. But we've already used 1 for 97, so this is going to be 122. So there is little z. This is what we're going to focus on in this lecture. Sure, we can do a whole bunch of this stuff, but we're just doing the basics of ASCII. Okay, now before we move on to our first problem, this probably made some people mad. Why is 65 A, capital A, and 97 lowercase a? Well, it just so happens that 65, if you convert it to binary, and I'm not going to go through all that trouble right now, but it ends up being 1, 0, 0, 0, 0, 0. I think there are 1, 2, 3, 4, 5 zeros there. And then a 1. So this is base 2. And 97 is 1, 1, and then 4 zeros, and a 1. So that's base 2. Now we can pad this out by putting a 0 in front of it. Now why would I do that? Because then there are 8 bits, so each of those is a byte. Okay. So this byte represents 65, and this byte represents 97. Why they chose to do that? Well, they didn't want the very first few numbers to start the alphabet because those are your control numbers. We don't, you know, for emergencies or whatever, we'd like to not have the lower numbers be letters of the alphabet. But watch this. When you go to cover up the first 2 bits, look at little a. That binary number 000001 happens to be 1. And then the next binary number, which would be 000010, that's 2, which is B, the second letter of the alphabet. Now, the lowercase letters have a 1, and the uppercase letters have a 0 there. So you know which one you're looking at by this or this. And so we can look at the lowercase letters by covering up the next bit, and so 00001 happens to be 1, which corresponds to A, and 2 would correspond to B, etc. Now when we add these other 3 bits in there, you know, we have numbers that are higher, like 65 and 97, but that's why I believe they started the alphabet uppercase at 65 and lowercase at 97, because they were natural. When you cover up the first 3 bits, it's almost like you're starting at 1. Some of you didn't want to hear that, but other people, they always ask, well, Joe, well, why do they do that? It's because it made a lot of sense. Okay, let's go ahead and do problems that you would see in your book. I know some of you are still kind of intimidated. You're like, whoa, what is happening? But just remember, your computer, like, you type up a history paper and you turn it off and then you turn it back on, your history paper is still there. What gives? Why didn't it get all erased? Because there's little switches, and each time you hit a button on the keyboard, that's a byte, and it stores it into those switches. And so your computer holds all the information in terms of, we'll simplify this, zeros and ones, whether your switches are in one configuration or another configuration. And so if this were a face-to-face class, this is what I would do. I would say, on your test, that would be the information that I would give you. 65 is capital A, 97 is little a. Translate the binary code to English. Okay, so here it is. Wow. We have 1, 2, 3, 4 bytes. So what I'm going to do is change each of these base 2 numbers to base 10. I'll show you 2 ways of doing that. The first way is what a lot of people would do, and then the second way is more of an efficient way. And then we'll get into the ASCII. So let's see what the base 10 numbers are for those. So the first way is, well, you know, this is base 2. Let's change it to base 10. So there's your 1's place, your 2's place, 4's, 8's, 16's, 32s, 64s. And then 128, I'm not going to write because there's a 0 there. And notice there's a 0 in front of each of those. So we don't have to even consider 128. Then the next thing we would do is we'd say, well, look, there's 164 plus 032s plus 016s plus 08s plus 04s plus 12. And so what I'm getting here is I'm getting 66. Then I move over to this one right here. So here's my 1s place, 2s, 4s, 8s, 16s, 32s, 64s. I know I'm writing pretty small. Hopefully it's not a blur on the video. And then I have a 64. So everywhere there's 1s, I put the number. 32, an 8, and a 1. So what do I have here? 10 and then 15 carry the 1. 6, 7, 8, 9, 10. So I have 105. And then we continue. 1s, 2s, 4s, 8s, 16s, 32s, 64s. Okay, so I have a 64 and a 32 and a 16 and a 4. So we add these up. This is 10 and then 16 carry the 1. 6, 7, 8, 9, 10, 11. Okay, so this is 116. And then this last one here, 1s, 2s, 4s, 8s, 16s, 32s, 64. So we have 64, 32, 4, and 1. We're going to add those together. This gives me 8, 9, 10, 11. Carry the 1. 6, 7, 8, 9, 10. And so there we have it. We have a 66, a 105, a 116, a 101. Now before we move on to changing those to the letters, the other way, you know, because you'll be doing your homework and you'll be like, wow, I had to write those red things 4 times. And if the word is longer, then I would have to write those even more times. So this is how I would do it. I would go 64, 32, 16, 8, 4, 2, 1. So I wrote what I wrote in red 4 times, but I just wrote it 1 time. And you know, if you're doing your homework, lots of times the first thing you do is you copy the problem onto a piece of paper. So I wouldn't copy the problem directly. I would say, okay, now I'm going to start copying the problem, and then I'm going to line these guys up vertically, and it will make it a lot easier. So this is 0, 1, and then 4 zeros. What? Oh, it's because of that. Let me just go ahead and put a 128 there. Okay, so I've just messed this up. Okay. And then some of you are like, great way, Joe. Yeah, you're selling me on that. Yes, I am. Okay, so there's a 1 there. Okay. 1. Okay. 4 zeros and then a 1 and a 0. And then the next one. So yeah, I would put the 128s just because, so you don't do what I just did there. So I have 0, 1, 1, 0. I'm copying this one, by the way, and then 1, 0, 0, 1. And then I have 0, 3 1s, and then 0, 1, 0, 0. And then the last byte here is 0, and then 2 1s, 2 zeros, 101. And then I would just go ahead and convert these the same way I did there, but now I don't have to write those numbers, those red numbers, 4 times. So I have a 64 and a 2. Now, some of these you can just do in your head. 64 plus 2 is 66, and we've already done this. And then this one right here, if you have to write them off to the side, great. This is going to give me 96 plus 8. That's going to be 104 plus 1 is 105. And so if you had a lot to do by hand, hopefully you won't have to do any of these things by hand ever again in your life after this class. We have 64, 30, so you just add them up like before and you would actually get the same answers. We're doing the same thing, except I'm showing you that this is a little more efficient. Okay, so now the next part is figuring out what these numbers mean. Well, I have a 66, and look, that's the next letter for uppercase letters of the alphabet. We know that 66 is a capital B. So it's a 4-letter word that starts with a B. Now, for these other ones, I just have to write out numbers that go all the way up to 116. So 97, 98, 99, 100. So I'm going to 116. This is me being lazy. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, and then the fun part. Twinkle, twinkle, little star. Is it twinkle, twinkle, little star? Twinkle, twinkle, little star. A, B, C, D, E, F, G. Yep, so we just, whatever, sing the song if you want. A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T. Okay, so let's see what this word is. 105. 105 is an I. Little I, lowercase I. 116 is a T. And 101 is an E. Translate the binary code to English. It is the 4-letter word that starts with a capital. It's byte. Okay, not the same as byte being 8 bits, but this is like maybe you're chewing your food or something, or you're eating. And so that right there, just a little tiny word, is all those zeros and ones. So imagine when you do a 20-page or a 100-page paper for your English class. That's lots of bits, but computers can handle it. And so your computer will store all your information in terms of zeros and ones. In fact, that's how your camera works. When you take a camera, the pixels are represented by numbers, and that's how photos and even videos are stored digitally. It's all zeros and ones. And we don't want to get into photos and videos in this class, because then we're turning it into a computer science class. We don't want to do that. Let's go ahead and do the next one here. So in your homework, they'll ask you to translate the English word to ASCII. Leave your answer in base 10. Okay, so that's going to make it a lot easier. So all we have to do, here's the word 1. So now I have to actually go to capital O on the alphabet. A, B, C, D, E, F, G, H, I, J, K, L, M, N, O. Oh, the song's so fun, P, but I'm running out of room here. So this is 65, 66. You know, I'm not going to even write down all the letters because I'm lazy. 67, 68, 69, 70, 71, 72, 73, 74, 75, 76, 77, 78, 79. So the O is a 79. Now, if you're doing your homework, you might just want to have them all written down if you have to do a few problems, so you won't have to do this for each problem. I know on this one I have to go to little lowercase n. Okay, so little n or lowercase n, A, B, C, D, E, F, G, H, I, J, K, L, M, N. Okay, I'm there. I used to think, well, a lot of kids think when they first learn the alphabet, you have elemento. So you thought mento. Well, I thought mento was a letter. I was like, mento. It's also a candy. So here's 98, 99, 100. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is 110. And the E, oh, whoops. Okay, so this is, I should have labeled it 98, 99, 100, 101. So in your homework, when they say translate the English word to ASCII and leave your answer in base 10, well, we're pretty much done. We're going to write, our answer is 79. N is 110. We'll put commas in between them, you know, just so we can say, oh yeah, that's the first one, that's the second one, and the E is a 101. And so there it is. That's really a basic understanding of how computers work. I mean, I shouldn't even say that, but now when people say, oh, it's all about zeros and ones, you won't be as confused. You'll say, oh yeah, I know what that's about, and I've even translated some words to ASCII and some ASCII written in binary to words. So let's go ahead, before we finish off this lecture in 4.4, is show you that in the real world, sometimes they make mistakes. Okay, so what I'm going to need before I get there, LMNOP, Q, R, S, T. I just didn't have room, so I had to put it over here. 79, 80, 81, 82, 83, 84. So this is 84. So I want the capital T for some reason. And I also want to note that this C is a 67. Okay. So the reason I'm going to do that is, back in the 1970s, they made something called Schoolhouse Rock. And I think this is from the early 80s. I can't show you the video, but I'll show you a snapshot. And this is all we really need, is this right here. And they're showing this little kid. So they thought with Schoolhouse Rock, oh, the education in America stinks, so let's try to motivate kids on Saturday morning by showing them cartoons about learning. Right. Well, anyway, so this one right here, we have, they're showing this kid about ASCII. And they're not really getting into it as much as we got into it. And this computer can talk and all that stuff. And he's saying, well, look at this is cat right here. So let's just check it out here. I'm going to convert this binary to base 10. So look what we have. We have 1, 2, 4, 8, 16, 32, 64. So notice how the 64 place we have 1, 1, 1 there, and then on the 32 place we have zeros there. And we could have said that right here. On the 32 place I had a 0 here and then 1 there and a 1 there and a 1 there. That told me capital letter, lowercase, lowercase, lowercase. That's exactly what I had. So it's always the 32 spot that tells you whether it's going to be capital or lowercase. These are all going to be capital letters. So let's figure out what this is. This one right here is 64 plus 2 is 66. This one is 64 plus 1, that's 65. And these were animated cartoons, and animation cost a lot of money. So let's see what happened. This one's going to be 64. We're just verifying their answer here. 64 plus 16. I better write that down here. I don't have a calculator. Plus 16. Plus 4. Okay, so that one gives me 14. Carry the 1, 6, 7, 8. 84. Okay, so let's see if we can get this here. 66 is B, 65 is A, and 84 is T. Oh, I'm so upset with Schoolhouse Rock. Look at this. We're trying to teach the kids in the 1970s because, you know, we had disco and drugs and just bad things were happening. And look, we can't even do that. This could have been part of the drug effect with the animators or whoever was doing this. So, oh well, there is our mistake. Anyway, we are finished with 4.4. Do your homework. Have a good day. I'll see you in the next video.